Okay, so I want to give just work through the solution for the geosynchronous satellite. So we have Earth observing satellite. It's put in geosynchronous orbit. So it means that its orbit is matched to the period of the Earth. And so what that means in practice, right, is that if we have the Earth here with its radius, and let's say that's our North and South Pole, and the Earth is spinning. That. So there's some satellite that's going to rotate with the same angular velocity as the Earth so that it would always be above the same point on Earth. And it's easiest probably just think about it from the equator perspective. So this satellite is going to have some radius different from the radius of the Earth, but it's going to have a period or angular frequency that is equal to the Earth. Okay, so here's our little satellite out here. Looks like a bug. Okay, so let's think about this. Whenever you're seeing an object going in a circle, right, it's going to be a circular orbit. We want to think about the equation, right, that there has to be a net force moving in the circle. And from this is really a gen phys problem, mv squared over r is the net force in the radial direction. So if we look at a free body diagram of our satellite, all that our experience here is the gravitational force from the Earth. Okay, the Earth is pulling on the satellite, keeping it in orbit. Remember from Gen Phys, like it's a top-down view of the buggy, right? The buggy needs that string attached to go in a circle. If we cut that, it's just going to go off in a straight line. Okay, so when an object moves in a circle, there has to be a net force toward the center of the circle, and the value of that force has to be mv squared over r. So from our free body diagram, we know this is just Fg is mv squared over r. Now the problem also is framing it in terms of omega. So remember that v is omega r. So another way to write this, which actually we talked about as a centripetal force, if we plug in omega squared r for v, we get m omega squared r squared over r. So m omega squared r is another way to write the centripetal force. Okay, so we're almost there then. So we have expand out our force of gravity here. So g, mass of the Earth, mass of the satellite, divided by the radius of its orbit squared. And then mass of the satellite, its angular frequency squared times the radius. Okay, so mass cancels out. And we are trying to find the height of the orbit. So actually, we want to know r. Okay, so let's bring r over to the one side. So we multiply by r squared, so we get r cubed over here. And then I'll divide by omega squared. Gme over omega squared. And now we want this to be the same angular speed as the Earth, so we'll put omega e. And then we're almost done. We just need to take the cube root. So r is the cubed root of g me over omega e squared. Oh, cubed. Sorry, omega e squared, but we need the cube root. Okay, so what do we need to recognize here? You need to recognize that the satellite is just undergoing circular motion, that centripetal force is provided by the force of gravity, right? The rest is gen phys. Okay, that's it.